Yeah.
Our next speaker is Eric Lopez from the University of Edinburgh.
Thank you very much. So yes, how I, formerly of Santa Cruz, where I did my PhD, I'm now a postdoc at the University of Edinburgh, as you rightly note, on a EU grant. Fortunately, I did get an email this morning. I am not out of a job. I do still have money for, it's not going away. However, let's see, is this the clicker or is, sorry, I should have asked that sooner. No, I just got the laser pointer.
Okay.
Yes.
All right.
Ah, okay. I can just use the arrow as well. Okay. Sorry. Can you tell I'm a theorist? Okay. So yeah. So obviously, this was not a happy day for me. If any of the Brits in the audience are in need, I did bring a nice bottle of Dalwhinnie with me from Scotland, so come see me later. But hopefully, I think I can distract you for at least a couple minutes with what I think is some fairly exciting science. So later in the meeting, I think I'll actually talk a bit about the inflated hot Jupiters, but mostly what I work on are the hot, short period, low mass planets and trying to understand their evolution, particularly with evaporation, as we've heard a lot about this week. So just a quick outline. I'm going to start with just a quick bit of background and motivation on super-Earths, sub-Neptunes, and evaporation. We've already heard quite a bit about these planets, but I want to sort of talk about broad strokes of what are the general features of this population and what can evaporation, how we can use evaporation as a tool to understand this population in general. Then I'll go just a little bit into how we model planet evolution to take into account for this physics. And then I'm going to focus in particular on what I think is a very interesting and useful population of planets, the ultra-short period planets. These are the newly discovered planets that have orbital periods of less than a day or so. And I think these planets are incredibly useful. And then finally, I'll describe quickly some results from some evaporation models I've run that I'm hopefully about to submit, and then discuss the implications for planet formation. So I think from the Kepler mission, one of the most important things we got is an idea of, for the first time really, of how common different sizes of planets are. So this is the corrected occurrence rate, corrected for selection effects, for planets within about 85 days. So for non-astronomers, this is about the orbit of Mercury. And this is planet radius compared to the Earth. So for comparison, Earth is down here. Neptune is about 4th radii up here. Here you can see the occurrence rate. So giant planets close in, while very fascinating, are quite rare. But then once you get below about the size of Neptune, planets become incredibly common. And the big question is, okay, down here, we all hopefully have some idea of what an Earth-like planet could potentially be like. We have at least one good example for that. And we have 2 examples in the solar system of what a Neptune-sized planet can be like. But what on earth are these things in between? These are called super-Earths and sub-Neptunes. We know from follow-up work that somewhere at around 1.5 Earth radii, you find a transition between bare rocky planets and non-rocky planets. As James was saying earlier, planets that just from their densities alone have to have a massive gaseous envelope. And just to be clear, I'm not talking about an atmosphere. I'm talking about things that make up a significant component of the bulk density of the planet. So I think one of the key questions is going to be asking, what on earth can that bulk component be? Jonathan showed this figure on Monday. So don't worry too much about the actual data at the moment. That's all of these points. I've sized them inversely to their precision. So these are sort of, as of right now, this is our population of low mass planets that we have good masses for. But as Jonathan pointed out, there's this interesting degeneracy where down here you have the bare rocky planets. Up here you have the sub-Neptunes that have to have large volatile envelopes, but there's a degeneracy. They can have a 1% hydrogen-helium solar composition envelope, and that can explain their size. But they could also have a significant water steam envelope that is, say, half, 70, 80% of their mass, and you get a planet with roughly about the same size. So it's two wildly different compositions, but from mass and radius alone, it's impossible to distinguish between them. And of course, this has huge implications for planet formation. As we all know from Planet Formation 101, if something contains large amounts of water ices, then it probably formed very far out, or at least some of its material formed very far out beyond the snow line, and then had to migrate in. Remember, I'm talking about planets that are on less than 85-day orbits. A lot of these, in particular, I'm going to be talking about planets on one-day orbits. So if they are large amounts of water, that means these planets could not have formed in situ. They had to migrate a huge amount. On the other hand, if these are just scaled up Earths, if they're just scaled up Earths that in some cases have a bit of a hydrogen envelope, then you can imagine them forming closer to in situ. And this is a very important distinction. It has huge implications for habitability, for Eta Earth, for all sorts of issues. So that's what I want to try and address. I think going about that, evaporation is a really useful tool for trying to break degeneracies in planet composition. Because of course, as we've heard several times this week, if you take a planet with a gaseous envelope, you stick it on a one-day orbit, you're going to get a huge amount of evaporation. And now for gas giant planets, as is pictured here, I think Andrew also had this very nice artist conception on his title slide, you get this huge cloud of gas coming off in Lyman alpha that can be observable. But if you're hot Jupiter, you may be losing an Earth mass a gigayear. Well, you've got 300 Earth masses to spare. What do you care? It's amazing, it's observation, it constrains a lot of physics, but it doesn't really affect the planet. On the other hand, if you're a sub-Neptune and you only had maybe 1/10 of an Earth mass to begin with, then you're talking about transforming the planet. You can take a sub-Neptune, put it on a one-day orbit, and you strip it away, and all you're left with is this burnt-out rocky husk of its former self. And so what that means is that the compositions we measure today, at billions of years later, do not equal the compositions at formation. But that evaporation is going to depend on what the planet is made of. So I'm going to try and use that evaporation to break those sorts of degeneracies. We have really nice observational evidence that I think is very suggestive this population has been, on the whole, strongly sculpted by evaporation. I think we saw this figure on Monday and then again later in the week. Here I've just plotted what is the total XUV energy planets have received, integrated over their lifetime with some nominal scaling relations, mostly for sun-like stars, versus the planet's binding energy today. I've color-coded the planets by what their composition is today. So these rust-colored planets are meant to be bare rock, hence why I tried to color them vaguely rust. And then all the rest of the planets are things with gaseous envelopes. So the idea is here's the energy in, here's the energy you have. Therefore, there should be some sort of, if evaporation is going on, there should be some sort of a threshold in this figure. And chi by eye, that's what I see when I look at this. I see a nice threshold above which you do not find planets. You do not, for example, find planets that are 2 Earth masses and 5 Earth radii that are on a one-day orbit. Those don't exist. Those would be up here. You do find these bare, burnt-out rocky worlds on one-day orbits. And you do, by the way, down here, this is where the superpuffs live. Interestingly, I first made this figure, I think, in my 3rd year of grad school, and I keep updating it regularly. The superpuffs keep piling up right on the threshold, which always I find very interesting. But I think overall, this paints a convincing picture that evaporation has been very important. Just for those who are curious, I think this is very relevant to Laura's project. This is where the M dwarfs lie. This version of the figure is a little bit older. This is from my thesis, so you'll notice a couple of planets disappeared. But this is GJ 1214, this is 3470, and this is 436. For reference, more recently, this is where GJ 1132 would lie. And if you assume they're rocky, TRAPPIST 1, B, and C would also lie about there. And so there's this interesting observation that if you look at the planets around mid to late M dwarfs, where the stars are much more active, sample size of 6, but they seem to be more vulnerable to evaporation than this population defined by sun-like stars. So it's just a modest suggestion that I think is still very suggestive and really motivates some projects like what Laura is working on. So okay, I don't want to get too bogged down in the details of the model. I'm happy to take questions later. For the full details, you can take a look at our 2012 or 2014 papers. But the basic idea is you take a model of how the planet evolves thermally in time and how it loses its mass over time, and you couple the two together. So this is the thermal evolution. This is just basically your standard stellar structure evolution model. You have some interior entropy. You want to know how that evolves in time. So you model the radiative transfer through the atmosphere, or you get Jonathan to do it for you. And then if you're a low mass planet that 90% of your mass is in the core, you probably need to model the radioactive heating and the cooling of that core as well. And that's basically all that goes in there. There's a lot of details, but the end story of this is you can then predict for a given planet mass and age and level of radiation and composition how large a planet should be under the influence of thermal evolution. And then you go and you combine that with a model of planet evaporation. For today, what I'm going to be doing is I'm going to be looking at two different mass loss regimes. So Ruth mentioned earlier in her talk, there's this energy limited regime, which is generally valid for things that are sort of moderately irradiated, the things that sort of tens of day periods. When you get to these one-day periods, you have to worry about radiation recombination cooling. And so you enter a different regime. This is from Ruth's 2009 paper. What I'm going to do, I'm going to compute both of these mass loss rates, and then I'm just going to take whatever is lower. And that does a pretty good job of, at least for planets sort of on tens of day orbits and less, for solar atmospheres, modeling this sort of full behavior. Okay, now just one other caveat I want to point out. All of this evaporation happened very early, as James was talking about. It's always important to remember the sun was a factor of 100 brighter in the extreme UV and X-rays when it was less than 100 million years old than it is now. When you combine that with the fact that planets' radii were much larger when they were young, because of course they still have all of that heat from formation, that means almost all of the evaporation happens during a planet's first 100 million years, and today we're just seeing the aftermath of that train wreck. So now I sort of want to jump right into the results. So I have this evaporation model. You can run a giant suite of models, and what that allows you to do is to predict where planets should end up in terms of their radius and their envelope fraction as a function of irradiation. So this is just a giant suite of models I've run. The thing I want you, the colored points of the individual models, color-coded by their envelope fractions, the thing I want you to pay attention to is this grayscaling. That's telling you where the models pile up. So where it's darker, more models. So over here you have the population of the sub-Neptunes that still have a gaseous envelope. Down here you have the stripped rocky super-Earths. Here I've assumed everything has some initial envelope. I'll assume it's a power law distribution, but everything starts with an accreted envelope. And you make the rocky super-Earths by stripping them. Interestingly, you'll note in between here you have a bit of a gap. This is the so-called evaporation valley, which ask me about later. I think it's very interesting. But I'm running out of time, so I want to jump straight into the ultra-short period planets, because I think these are incredibly useful. So this is from a Nature paper from earlier this year by Lundquist. This was noticed earlier than that by Roberto Sanchez Ojeda. There's this interesting observation that if you look at the planets within orbits less than 1 day, they're all consistent with being rocky, to first order, with maybe one exception. They're pretty much all consistent with being rocky for the planets less than about 4 Earth radii. There just aren't sub-Neptunes on orbits less than 1 day. And this is, of course, what you might expect if planets formed with a hydrogen-helium envelope. Hydrogen-helium envelopes are incredibly vulnerable to photoevaporation. So you stick them on a 1-day orbit, they're just going to get ripped apart. If you try and make them so massive they can resist that, they'll tidally fall onto the star. So this is that same figure I was showing you earlier of the distribution of radius versus flux, but I've shifted to higher radiation. So here for comparison is 1 day. And what you'll notice is basically very, very, very few planets survive with hydrogen-helium envelopes. Basically, I think I ran about 10,000 models to make this, and basically everything ends up rocky. However, and this is the key caveat, this is not true if you talk about planets with steam atmospheres. If you have I'm going to go to the other limiting case. No hydrogen-helium, it's just a pure steam atmosphere. In that case, planets are very resilient against evaporation. And this doesn't even really matter what exactly evaporation prescription you use. A lot of this is just because the thermal evolution of a steam envelope, the radius doesn't change anywhere near as much in time. And so this makes a clear prediction that if the ultra-short period planets were mostly forming from material that came from beyond the snow line and was very water-rich, then there should be a large population of them that are still have retained their steam atmospheres and are over 2 Earth radii. And that is not what we see. And I think, yes. And here are my conclusions. Tad, okay. Sorry, Tad? Yes, sorry. So that is at 5 gigayears. It doesn't, once you're beyond a couple 100 million years, it doesn't really matter. But yeah, that was at nominal age of the solar system. They reach a steady state envelope fraction. The radius continues to contract a little bit, but that's just from the thermal evolution. I think I saw George first, and then Mike. Yes, so one key here is, in this figure, I'm only including the steady state XUV heating. This is really there have been a big effort with HST STIS and with things like Chandra and XNM to constrain the high energy heating for sun-like stars and to some extent down to about M2 or so. But STIS observations are of course expensive, so they don't want you to stare at a single star for a year to see how it's varying. So usually we just get a quick snapshot and we get some idea of what the steady state emission is. And it roughly seems to follow a similar power law from early M to late F or so. This does not account for flares. And I think that could be what's going on here. Because once you get around mid-M dwarfs, that's going to be very important. I think Mike first. Yes, I am very interested in 55 K3. I've thought a lot about this. If you put a hydrogen-helium atmosphere, and I think James can back me up on this, it's gone instantly, within 1 million years. It cannot retain to a hydrogen-helium atmosphere. It's really weird. I don't understand how it can be a bare rocky planet. It should be a water envelope, I think, but then how do you explain what's going on with the variability and the day-nights, if I'm to trust observers? Yeah, I'm curious to talk about. We can talk about this more later. I don't know what to make of it. But no, it cannot, 55 cancri cannot hold on to a hydrogen-helium atmosphere. I think Daniel and then James. Oh, yeah, it will. Before the evaporation happens, I think the evaporative wind Ruth showed is generally launched at around a nanobar, down at about the microbar level, or so you've already further dissociated the water. But the dissociative heating isn't anywhere near as intense as the ionizing heating. So it's the ionizing heating that really does the work to remove material. Yeah, James? So for that, I think I used Eugenia Skolnick and Travis Barman. They had some relations. The caveat is we have good observations of the FUV flux, I believe, and the X-rays. We don't really know what the EUV is doing, so the standard thing is just to assume it scales the same way with stellar type and age. So that's what I did, sort of basically using the same sort of relation that is applicable for early M and sun-like stars. You do get a little bit of enhancement because what's actually constant is the XUV to bolometric ratio, and you get a lot of evolution in the bolometric luminosity because the pre-main sequence lifetime is so much longer. So that does give you an enhancement. I include that.
Thank Eric again.
Fairly exciting science. So later in the meeting, I think I'll actually talk a bit about the inflated hot Jupiters, but mostly what I work on are the hot, short period, low mass planets and trying to understand their evolution, particularly with evaporation, as we've heard a lot about this week. So just a quick outline. I'm going to start with just a quick bit of background and motivation on super-Earths, sub-Neptunes, and evaporation. We've already heard quite a bit about these planets, but I want to sort of talk about broad strokes of what are the general... Yeah.
Our next speaker is Eric Lopez from the University of Edinburgh.
Thank you very much. So yes, how I... formerly of Santa Cruz, where I did my PhD, I'm now a postdoc at the University of Edinburgh, as you rightly note, on a EU grant. Fortunately, I did get an email this morning. I am not out of a job. I do still have money for, it's not going away. However, let's see, is this the clicker or is, sorry, I should have asked that sooner. And then finally, I'll describe quickly some results from some evaporation models I've run that I'm hopefully about to submit, and then discuss the implications for planet formation. So I think from the Kepler mission, one of the most important things we got is an idea of, for the first time really, of how common different sizes of planets are. So this is the corrected occurrence rate, corrected for selection effects, for planets within about 85 days. So for non-astronomers, this is about features of this population and what can evaporation, how we can use evaporation as a tool to understand this population in general. Then I'll go just a little bit into how we model planet evolution to take into account for this physics. And then I'm going to focus in particular on what I think is a very interesting and useful population of planets, the ultra-short period planets. These are the newly discovered planets that have orbital periods of less than a day or so. And I think these planets are incredibly useful. Oh. No, I just got the laser pointer.
Okay.
Yes.
All right.
Ah, okay. I can just use the arrow as well. Okay. Sorry. Can you tell I'm a theorist? Okay. So yeah, so obviously this was not a happy day for me. If any of the Brits in the audience are in need, I did bring a nice bottle of Dalwhinnie with me from Scotland, so come see me later. But hopefully, I think I can distract you for at least a couple minutes with what I think is some